Hello guys, welcome back. And this is Harsh, and today's topic is Dijkstra's algorithm. So basically, Dijkstra's algorithm is used for finding shortest distance between any two vertices in a graph. Basically, for weighted graph, mostly it is used because for unweighted graph, there are easier way to do the same thing. So now here is our graph, and as you see, it is an unweighted graph. So I have been going through Geeks for Geeks and I have gone through the algorithm. And let's try to implement Dijkstra's algorithm. So basically, Dijkstra's algorithm which we would be implementing for graphs is based upon the adjacency list representation of the graph. As you know, the graph can also be represented using adjacency matrix, and this would be using a greedy approach, our algorithm. So let's go ahead and start. So for this we would like first need a graph. So let's create a weighted graph. So as you can see, there are two classes which I implemented in my project. So one is undirected graph, but we would be using Dijkstra's on the weighted graph. So let's create an object for that. Let's call it undw, and we can either create this graph, but I have went ahead and I have already created a static method to add all these nodes uh, to my graph so that we can save some time. And I will just show you what I have done here. So simply added all these nodes and I am returning the object. Okay, so this is the same example I'm using from the Geeks for Geeks. What we can do first is probably we can print this graph to see if we have added all the edges properly and the weights are correct. Let's run this for now. Let's just quickly compare it with the graph. So 0 is connected to 1, yeah, and 7. 1 is connected to 2 and 7. 1 is connected to, yeah, 2 0, 7 and 2. Then 2 is connected to 1 and 8 5 3, yeah, 1 8 5 3. And node 3 3 is connected to 2 5 4. 2 is connected to, sorry, 3 is connected to 2 5 4. 4 is just connected to 3 and 5. 5 to 6, 2 3 4, yeah, 6 4 3 2, yeah, and 6 is connected to 5 7 8, and 7 is connected to 0 1 6 8, and at last 8 is connected to 2 6 7. So yeah, so we have added all the nodes properly, and we can start implementing the Dijkstra's algorithm. So I would be implementing this in my heap utility static class. Let's call this function and what I want to pass here is I just want to pass the my graph and a source from where we want to create the find the shortest path to all the other vertices in the graph. Probably at later stage we can include the destination also, because first we want to create an algorithm which will create the shortest path between each and every node from the source node. So I selected 0 as my source node, but it could be 5 or 6 or 3 or 4, anything, right? And what we want to do here is in this function we want to uh, find the uh, shortest path between the source node and all the other nodes in the graph. So yeah, let's go to, oh sorry, yeah, I want to create it in graph utility class, not my uh, other class. And this was the I was telling you about to find the shortest path in unweighted graph. This was another video I made yesterday. You guys can check it out on my channel. So it's quite similar to the unweighted graph, how we calculate the shortest path in that, but it has some difference. So let's see if you would be able to implement it successfully in one go. Let's call this UG only, UG table. So first thing what I want to do is just check if whatever I am passing it's not null. So here I am checking if my graph is not null, or if it is not null, then the array which is used to implement the graph, that is also not null. If it is null, we just return from here. So now okay. So what is required for this algorithm? So I was going through the algo. The steps are like mentioned there. So basically, what we need is we need to go through each node and traverse the each node, and then what we do is all its adjacent nodes, we put them in our priority queue, and we put them in such a way that the distance between that node and its node is added as a key, and the node index is added as a value. Why we do that? We are doing that so that whenever we are getting the the root of our priority queue, it will always return us the shortest distance between all the adjacent nodes of of a node. For example, for if we are traversing for 0, so we would be adding 1 with the priority 4 in a priority queue, then we would be adding 7, and we would be adding that with the priority 8. So, and after this step, if you will do the get min or extract the highest priority in a priority queue, it will return us 1, because that is the shortest distance, and that's why the key in our priority queue would be the distance between the nodes. Okay, and we would be needing one more array and to just store the distances between the source node and the all the nodes, and we will be using that array to store the distance. And I will also create another array which would be using we would be using to find the path. Suppose if I want to find the shortest distance between 0 and 2, so it would be like oh, let me check, 472. yeah, so it would be 4 plus 8, which would be 12. But I also want to on later stage print the path, like how did we get this distance. So it would be 0 to 1 to 2. So we will solve that part later. First, just focus on finding the minimum distance between the two nodes. So we are in that. Now we want to create a priority queue. Okay, we will just name it the queue, and size would be the number of vertices in our graph. Right. What else we need? As I mentioned, we would be needing a distance array. I will create a simple int array. I'll call it distance. Again, we have the same length, as we just need it would be the same length as number of vertex in our graph. And also I discussed we would be creating one more integer array to store the each node's previous nodes, like how did we came to that node. So like that would be helpful in later stages, and when we would be trying to print the path, how did we get that shortest distance between a and b node. So for now, let's just create it. Now what we do want to do here is, for all the nodes, I would like to update the distance for each of those nodes as -1, and that would be helpful at later stage when we would be traversing through the graph, so that we know what all nodes and vertices we have already calculated the shortest path for, and we need not calculate again. So I would be initializing that with -1 to indicate we have not traversed the graph a particular node, and if it would be anything else other than -1, then it indicates the shortest distance for that node is already calculated and stored in a distance array. And I will just go ahead and also initialize the path for each index, which would be storing the previous node to that index as also -1. This statement will initialize both our arrays, all the indexes as -1. what I would want to do now is add my source to priority queue. And remember, what we would be doing here is we would be adding the priority and the value. So the priority for the source would be the highest, as priority basically here is our distance between two nodes. So for suppose zeroth node is our source node, its distance from itself would be zero, hence its priority would also be zero. So yeah, I'm just going to do that. And the second value would be the index, that would be source. And before this, I quickly want to, in the distance array, I want to update my source path to 0, right? As we discussed, a source is 0 distance from itself. Now what we ideally want to do is uh, traverse through the graph, and how we do that is we'll just check if our priority queue has any element left in it. So now the real part starts. So we have initialized all these things. So we have a priority queue which would be storing the distance between two nodes as the priority, and the index of the particular node as its value. And then we have the distance array which would be holding the minimum distance for each node from our source node, and the path which would ideally be storing the previous node which we encountered before coming to the current node, and this would be helpful when we would be printing the path from source to destination. And for the source node, we have already marked our distance as 0, and the same we have added in our queue, right? So what we do want to do here is we'll pull the node from our priority queue. So we want to extract the highest priority element, and for that particular element rather use for each. So what I want to do here is for each of my vertex, for each vertex I want to iterate through all of its adjacent vertex, right? Suppose if we are at 2, I want to iterate through 1, 8, 5 and 3. Right, we entered the index as the value, hence I am fetching that. And for that index in my graph array, which is like storing for each index, which means for each node it's storing all its corresponding uh, uh, vertices in a list, right? You will see the list of graph nodes. So graph nodes are basically our vertices for at each index. And what I want to do here is check if it is the node which I am encountering for the first time, or if it is a node which is already being processed earlier and we already have calculated the minimum distance for that node. How we do that is, in our distance array, we can check if the adjacent node value is -1 or not. So -1 would indicate we are processing it for the first time. And yeah, one quick thing I just forgot. So before checking the adjacent vertex, what we want to do is we also want to calculate the distance. Okay, and distance between the adjacent vertex and the parent. Okay, the node which we have put. Let's just call it parent. Okay, so distance would be, and how do we calculate the distance? The distance would be the value like the distance for the adjacent vertex from the source node would be the distance of its parent from the source node plus the distance between these two nodes. And for the parent node, we can find the distance from our distance array, right? Plus what we want to add here is the distance between the parent or the adjacent vertex. So how can we do that is, uh, let me just check. So at each node I am storing the distance. Yeah, this is one directed graph. Yeah, at each node I am storing the index and the weight, which is the cost or the distance in our case. And when I would be when I want, like what I'm trying to know here is how can I fetch the distance which I have inserted, which we have in our graph. So I'm just going through that. So node and so if I want to find the distance between a node 1 and node 2, I want to go to that node, and then I can just uh, at that node 2 I can just look for the uh, adjacent node which I want, and then once I get that node I can get its weight, right? And then let me just check in what all. So I'm trying to find the easiest way to get the weight here. So yeah, okay. I'll just pause the video. I'll resume once I find the method and let you guys know. Hi guys. So actually I was overthinking here. I just realized I need not fetch the weight for the parent and adjacent node from the graph. So at each node I am already storing the distance of that node, particular node from its parent node. So yeah, here I can just simply use adjacent vertex dot weight. So this will return me the weight for that node from its parent node. So yeah. So actually I forgotten about that. So yeah, I checked. So now why is it throwing error? Since yeah, this is of dot node. It's of type int. Okay. Sorry. I need to pass the parent node's index in my distance array. So yeah, this will give me the distance uh, for this vertex, adjacent vertex from the source. And how we calculating? So whatever is the distance of its parent from the source plus the distance between the parent and the adjacent vertex. So that is in dist. And now we are just going to check if this node, have we encountered this node, like or processed this node anytime in the loop. If not, what we want to do here is we want to first update the value. Yeah, so this is its key. That so in the distance array I have updated the adjacent vertex and I have fetched its index. And in its index I have updated the newly calculated distance. Okay. Yeah. And since we have now like uh, added this to our distance array as well, what we want to do next is we also want to add the adjacent vertex in our priority queue, right? So the priority here would be, of course, distance from source, and the value would be the nodes index. Let me just quickly go ahead and update it to nodes index. Yeah, it would make more sense. Okay. So we have done this in case we have never encountered this node. And what we have done is we have added its distance in a distance array, and then we have also added this node in our priority queue. And what else what we want to do is, and if that is not the case, so like if we have already processed this, like its value is not -1, that means like then it means we are properly, like we are we have calculated for 0, and then we have calculated for 1, and then we have calculated for 2, and then 8, suppose. And after this point we went back and we calculated for 7, and because that was the shortest distance at that point in the priority queue, and then we were calculating for 8. So for if this distance is smaller than the earlier distance, we also need to update that in our priority queue. So if for that node, suppose for that eighth node, we have not we haven't created or we haven't updated its distance, then we need to update it in our priority queue as well. So what we do want to do here is we need to check. Guys, just to let you know, this is my first time I'm trying to solve this, so it's not I have already solved this question and just recording it. So yeah, I am facing some difficulties, and I'm trying to record the session as realistically as possible. So these kind of error like you can also encounter. So I'm just recording to show my experience when I'm trying to solve this problem. So what I have done here is if the distance, yeah, if the newly created calculated distance is smaller than the distance which was earlier present in our distance array for this node, so then we need to update the distance. And the next step is we also need to update its priority in a priority queue. Since we haven't processed this node yet, so it can happen if before processing we find some other smaller path, smallest distance for a particular node, we need to update that as well in a priority queue. So here I would be doing update priority. Let's check what it requires. So data, it would be my distance. No, so I want to update the index. So here I want to pass the index. And the second parameter is the new priority, and which is by default set to the in.men. Here we have the distance. So that particular node, it would go and update the uh, distance in our priority queue. So yeah, what else we need to do? So we are not updating here anywhere that we have already processed this node. So what we want to do here is for the node which we have just processed, for that node, yeah, it's not required actually. The distance would be updated as and when we would be going through this node. Yeah, so the first node would came, and it's on adjacent distance would be calculated and there will be minus 1, so it would update and it will be added to priority queue and it will go out and again it will extract the topmost element. Yeah, I think they should be good enough. Let me just pause and check this once again. I think I had checked it again. It looks good. So let's just print the shortest distance now. We'll just now quickly update my function to accept a destination node as well. And here I will so let's path 2 for now. An easy example. Let's check this if it is working now. So the path should ideally be 4. So it's breaking. Okay, we will check this and next one out of point of that. So the path should ideally be 4 plus 8 2 because I don't see any other path which is closer than this one between 0 and 2. 4 plus 8 2 12. Okay, so let us check what is happening over here. So at this point I will just check. Yeah, distance for all the nodes is minus 1. Path is also minus 1. That is fine. And priority queue we just have our first node. Okay, and its key is the index, and of course the priority is also the distance from itself. So yeah, so the priority and key are basically the same thing. If you want to show see guys, I will just I have added two things to denote the same thing because sometimes it makes more sense to use the key and sometimes it makes more sense to use the priority. So yeah, so yeah, as I was saying, see, the priority and key are both the same thing. So coming back to our problem. So why was it breaking? Let's check this now. So we have our parent as 0, that is right, and we would be calculating the adjacent node for this, and what we have got here is 1 and with weight 4. So this part we are evaluating right now. So distance should come out to be 4, right guys? It's 4, and since it is not present, it's not already present, so we should be coming inside this. After coming in this if loop, uh, let's keep an eye the distance is being updated or not. So as you can see, the distance is updated correctly, and we are also enqueuing uh, the new vertex. Yeah, we need not go inside this. So at this point we have added one node. The second node should be added now. 7 with weight 8. 7 with weight 8. This is also right. So no more adjacent nodes are left. So we have processed 1 and 7, and the path in the distance array, we can you should be able to see 4 and 8 for 1 and 7. For 1 and 7, we have 4 and 8. So it has checked the priority key is not empty. What we would be doing now is extracting again the highest priority, which is the shortest distance from the source. So what we should get here is we should be getting 4. Sorry, we should be getting the first node now because it has the minimum distance now. So we have uh, got our 1, and its adjacent vertex which is being fetched right now is 0. Yeah, so since 0 is also the adjacent to 1, it should not go in this loop, inside this loop, correct? And we will be checking if its distance is smaller than the source node itself, which would be false, so it won't go because it would give the distance as 4, but the distance for 0 is already updated as 0, c0, and the current distance is 3, so which is not small, so it will come out. The next vertex which we are processing is 2. Yeah, this we are processing now. So okay, on node 2 the weight is 8 and its parent is 1, whose weight from the distance table should be okay, now I get it. Parent node dot value. So I made a mistake here, hence it was not calculating the distance correctly. The mistake was I was not fetching the index of the parent node. Instead, I was passing the priority of the key, which was the distance. So, but in distance array, we are storing all the distance from the source by their index. Let's run all of this once again. I think it should work. Yeah, let's print this. See what we got. Between 0 and 2 is 12. Is it 12? Yeah, it is 12. So, oh, guys, I think we have successfully implemented Dijkstra's algorithm. But just to be sure, let's check between few other nodes. Let's check between 0 and 8. So what should we, guys? We should calculate first, then we'll see the solution. 4 plus 8, 12. 12 plus 2 is 14. How else can we go to 8 from 0? It should be 8 plus 7, which will make it 15, or 8 plus 1, which is 9 plus 6, which is again 15. So ideally it should return 14. Yeah, that is right. Let's try one more example. Let's find between say 4 and 0. It says 21. Let's verify if it is correct or not. So we'll start, it was 4, and then 8, 12. Then from this node, if I see 4 plus 10 is 14, or 7 plus 9 is, yeah. So this is 14 and this is 16. So 4 plus 8, 12. 12 plus 4, 16. 16 plus 20 is, uh, oh, sorry, 16 plus 10 is 26. So, and another way we will try to see, if we go this way, from 0 to 7 is 8, then of course this seems shorter. So 0 to 7, 8, 8 plus 1, 9, 9 plus 2, 11, and 11 plus 10 is 21, and we got 21 correct. So that is how we can calculate the path, as like it was mentioned on the Geeks or Geeks. Let's go one step ahead, and also um, print the path. And how do we do that is, you remember, we have, as you guys remember, we have created the path array as well. So now you will be leveraging this. So here what I want to do is, when I'm like calculating the distance for a new node for the first time, I also want to update its path. And what I want to store is the previous node to this node. And what is the previous node? So the previous node is its parent node. Correct. So this way we would be updating the path, but we also want to do the same in case it's we have find another path which is shorter than the previous path which we have calculated. So this is also done here, and by the end of this we should be having the path for all the nodes in a path array. So if I will just use the past example which I used in my last video, and how to print the path, and I will just explain it now. So how are we printing the path from the source to destination is, sorry, so we are like backtracking. How are we backtracking? For 4, the previous node would definitely be containing 5, because that's the shortest path we got right in this array. And for the 5, the previous node would be holding the 6th index, and for 6 it would be holding the 7th, and for 7 it would be holding 0. So if you just backtrack from the destination and to its previous node and then its previous node's previous node until we get the source, so that should be the path. So here we are doing the same thing. So for whatever destination we were trying to fetch the minimum distance, we have fetched its previous path, correct? And then we have like uh, we are using stack here, and we are using stack because we want to print the path from source to destination. So the destination would be pushed first, right? And then the node prior to that, like 45670, and when we would be printing, we would be printing it from 07654 like this. And we can also use list here, and we can probably just reverse the list, or if you want you can print from destination to source. So, and while the previous node for the source, you remember it is -1 because here we have uh, uh, mentioned initialize the path array as -1 for all the nodes, and for the source it would be never be updated because it never goes through this part, right? So until we get the source, we would be pushing it to the stack, and then we would be updating the previous vertex to the previous of previous, correct? And then we would be just printing the vertex from our stack. Let's see, I hope it works. Yeah, so 07654, 07654, as you guys can see that it is implemented successfully. And this is how we implement Dijkstra's algorithm. This was my first try and it was nice, and uh, let me know in the comment section if you guys like it or not, or whether I should be solving the questions first and just then creating a short video with already having the knowledge of how I have implemented. Will that be helpful, or this way when I'm trying to find the solution after reading through the algorithm with you guys? Okay, and I would be also mentioning my GitHub profile, LinkedIn profile in the description. All the solutions for all the problems I have solved would be available there. Let me know in case you have any doubt. Thank you guys.